Okay. Okay, I think we're recording. Seems like we are. All right, folks. So official, welcome. Good morning, good afternoon, good evening, depending on where you're dialing in from. Welcome to the virtual Presto Meetup. This is our July edition. We're excited to come back. We're going to be doing more of these. We're going to try to do a lot more virtual kinds of events. I'll talk more about that in a second, but we're excited to have everybody here and to get you up to speed on what's going on from a TSC perspective from our chair, Tim, as well as a company called Compute.ai that's building a pretty awesome AI platform with Presto and some other things, and they're going to take you through a demo of that. But before we get started on that, just a few housekeeping items. One is PrestoCon. So PrestoCon is our marquee event. This is our in-person event. It's in December. It's going to be in the Bay Area at the Computer History Museum. The CFP is open. If you're a Presto user, if you want to share more about what you're doing with the open source project, we would love for you to submit a CFP. We are trying to get as much of the community involved as possible. So this is the link. I think, Arpan, if you can drop the link into the chat, that would be great. Of course, the registration's open as well. Tickets are on sale, but CFPs is open now. Highly recommend, if you're using Presto, submit a CFP. Okay, next. I'm excited to share we have Presto Community Office Hours. This is our brand new event, a virtual event that we're hosting. The first one will be next Wednesday, August 2nd. So what is it? This is going to be a very casual 1 hour. We'll probably do these once a month, maybe even a little bit more, depending on how many people come and want the help. But very casual. It's time for you to come, ask your questions. You can get help troubleshooting. You can meet with Presto engineers and other community members. It's very free. Drop in whenever you want, and we're here to help. So we're going to start these again once a month. We'll try to do them more if there's a lot more interest, but all the details are here. And we also have a link, which I can post in the chat after this, so that all the links will be available. It's just on our website as well, so you can add it to your calendar. But next Wednesday, 8:30 in the morning Pacific, and we hope to see many of you there if you need some extra. All right. So with that, I will stop talking. I'm going to pass it over to Tim, who will give us a TSC update and tell us what's been going on from the TSC perspective. So Tim, please take it away. You're muted too if you're, there you go.
All right, let me attempt to share my screen. Does everyone see the, oh, they're probably that's the wrong screen. So let me try a different screen. Okay. Now that I got the VC figured out, thanks everyone for coming. Just wanted to give some updates on the technical community within Presto and the investments that we're making to make it better. So first I'll go over why focus on the technical community, and then some of the areas where we're thinking of kind of improving the way that we kind of like interact with the community through concepts of ownership, communication, incentivization, metrics, and documentation. So we'll begin with like I guess like why focus on the community. So Presto had, since it's kind of like since it's been operated under the Linux Foundation, has operated under open governance principles. So that's sort of like been a fact since since the foundation was started. So that's obviously not changing. What we would like to change though is the way that sort of like we bring people into the technical community. And we would like to reduce the friction points in that and make it as easy as possible. So why do we want to do that? And the reason is code is our product. So the code inside the Presto DB repository is essentially the core of what we do, and the core of what makes Presto what it is. And vibrant open source communities have many different contributors from many different companies, and also encourage new contributions. And so for, to help make Presto an even better open source product, it sort of follows that you would want to make it so that you cast a wider net and bring more people into the community who themselves get ramped up and also help to ramp up others. So we want to encourage a more wider net in the Presto community and bring more people in. So, and some corollaries to that is more friction means less feature contributions. So the harder it is to get a PR into the the Presto DB repository, the less likely someone's going to be to open a PR in the future. The inverse of that is the less friction means more future contributions. And the reason for this is because several types of people come to open source. There's people who just like open source because it's something that they find interesting and they enjoy the public contributions aspect. Perhaps they work in a company that is mostly closed source, and this open source nature of their product is something that sort of fulfills a need that they have in their career. There are some people who contribute to open source because their employer actually recognizes it. So this, in particular, these would be people who use Presto. So, it could be a vendor, it could be a major tech company. And then finally, there's some people who, basically want to push more open source contributions because this is a pathway towards something bigger, like higher level influence in the project, such as a TSC role or less formal recognition in the form of being an expert in a particular area. So we want to, sort of like fulfill the needs of everyone who comes to the project, who, whichever path they come from. But, I think those are kind of like the major reasons why, people contribute to open source, and we want to encourage that and welcome that. Because it helps the product, it helps the project, and it, helps get more code. So there's the way that we're kind of like tackling this is, through several different, dimensions, and, trying a multifaceted, kind of like strategy for improving, some of the things that are sort of like creaking around the edges with the Presto project. The Presto project has been around a decade, and so, some things are, need to be updated, given current best practices and, given the current needs of the community. So the first one is, changing the way that we, basically, give out commit bits. So we're doing this through code owners. So if you open up the Presto project and look at the code, I think like the first thing that you're struck by is how much code there is. And often it's, very complicated code. And so it's, that really means that it's very difficult to get to be a general level expert across the whole project. And so, like this, it's been this way for years now, where typically people focus on particular areas. So we have people who focus on the optimizer, people who focus on the eval, people who focus on resource management and, reliability, documentation, user, the UI. And so, this really kind of like brings a natural way to change the way that we recognize committers by making it so that it's broken down by area rather than, sort of like a global permission. By breaking it down by area, it's easier to show mastery over a particular part of the code, and also kind of like tells people, what are the areas, so by having code owners for different areas, it's easier to figure out, just kind of like what are the we've kind of like already defined, what are the areas that you can, gain an entry to the project. And a secondary reason to do this is it's a really convenient way to evaluate slightly different bars based on, kind of like the contribution. So for example, the C++ contributions tend to be pretty different from the Java contributions. You look for different things just because the nature of the C++ code within Presto is pretty drastically different from the remainder of the Java code, which itself is very, very different from the JavaScript that we have in the UI, which itself is different from the documentation. And then, we are, essentially kind of like deprecating, new committers just because, we don't want two different tiers of contributions. Essentially, code ownership is the primary means by which someone gets a commitment. So essentially, code owners are committers. The second thing that we're doing is doing a better job of communicating sort of like what we're working on. So with a large project like Presto, you can imagine there's a lot of different threads that are going on in parallel, and a lot of these threads are happening by particular groups who have an interest in one particular area. So for example, Meta is very interested in batch, but it's very difficult to discover that based purely. You would have to essentially look at the commit history to kind of like discern that. What we're starting to do is leverage more GitHub boards and GitHub utilities to essentially show what is the current status of various different work streams and what are we currently investing in the project. I'll go over the kind of like the high level areas towards the end, but essentially these are broken down roughly by a rewrite of the eval engine, optimizer improvements, resource management improvements, and documentation reliability, and support for lakehouse formats. So we're starting to do a better job of categorizing this and showing the status of various different work streams through GitHub boards. We're not complete yet, but a lot of progress has been made, and I expect over the course of the next few months we'll have a fairly complete public view of kind of like the major initiatives in the project, but also areas that are not picked up yet and where people can help out without having to kind of like know what's going on. Ali already mentioned this, but we're also introducing office hours. Office hours are a great way to, sort of like pick the brains of, someone who's already close to the project, and have a more free-form discussion and, get a one-on-one setting to, kind of like talk about, essentially what's going on. We do have, community meetings every month, but those tend to be very structured. And the intent of office hours is to have unstructured, sort of like ask anything time so that you can just sort of like, get some unstructured insight into, the goings on of the project, or, even help operating Presto. We're also setting up a lot of working groups. And so the idea of working groups is there's various kind of like ongoing initiatives in the project that themselves are really huge. So for example, the C++ eval work is truly massive. And, we're going to have dozens of people, kind of like working on that. And so, the idea of a working group is to, number one, add a little bit more focus. So, something like the TSC meeting is, probably, too high level for, talking about the particulars of the C++ integration, for example. And so the idea behind working groups are twofold. The first is they're just great ways to pop into the project and, get information and visibility into one particular section, so it'll be less overwhelming, and hopefully like the name of the working group kind of like describes an area that hopefully also matches your interest, but then also bring a little bit more visibility into kind of like these major initiatives in a way that allows you to join in and kind of like join those discussions. So like we're doing this for a lot of major initiatives, such as obviously the C++ working group. We're having a general architecture working group to talk about, sort of like the, higher level architectural initiatives that are going on with the project. And we'll probably be spinning up a few more. And in addition, we have a working group for closing out security vulnerabilities and CVEs. And then finally, we're onboarding a mentorship program where the idea here is, for a few people, what we can do is essentially just give them dedicated support. And so, like we can't mentor everyone, but we can operate a program and evaluate people on a case-by-case basis, bring a few of them in, give them some dedicated support, and then hopefully fast track them for committership. The idea behind a mentorship program is not everyone has access to a colleague that you can just tap on the shoulder to gain insights into the project. And so the idea here is to kind of like open up that ability to tap someone on the shoulder to, folks who don't have that already, and sort of like kind of like broaden the net to more groups who would be interested in joining the foundation and the technical community. So that was on the communication side. Moving on to incentivization, what we would like to do is really highlight people who are doing a really fantastic job in the community. And so right now, some people are very diligent about reviewing code, responding to PRs and, kind of like doing pull request reviews in a really timely manner. And what we would like to do is just really kind of like highlight that and showcase it and hopefully kind of like incentivize that so that, more people kind of like know what the project wants and needs. And so, we're going to be creating a leaderboard in conjunction with the outreach committee, where essentially we'll be highlighting, the top end contributors periodically and, distributing swag for really awesome contributors. And then, perhaps even doing something special at the end of the year for the most awesome contributors. So details on that TBD, but that's kind of like a work in progress. And so then moving on to documentation, this is sort of like a more fundamental need, but like one of the frequent criticisms of the Presto project is that the documentation needs to be more clear, both at the code level and also, the user documentation. And so, we have some documentation engineers who are going through our Presto documentation and just making it easier to get started on Presto development, get started using the tools for Presto, and kind of like, basically encourage people to, get to PR submission without having to ask someone, by making the documentation just good enough that you don't really have to ask someone. The idea here is obviously, kind of like broaden the funnel so that if the documentation is good enough, less people just give up halfway, we get more PRs and we, get to, review those more quickly. And then on the code side, we're going to be adopting a campsite role for Java docs where, essentially, if you're modifying an adjacent, class, which is, kind of like relatively important, we'll want to add Java doc for that so that future people don't have to do the same reverse engineering and guesswork that you might have done when you made that code change. In terms of metrics, obviously, kind of like I think the adage that you can't improve what you don't measure really applies here as well. And so GitHub metrics are actually a surprisingly nuanced, a nuanced thing. But what we are doing is kind of like providing high level metrics on, overall, how is the project doing, and are we on a track that's improving or kind of like getting worse? I've attached here, like our current metrics, which definitely are trending up in terms of productivity. So that's on the activity tab. So, on average, we have a lot more commits, a lot more issues and reviews. This is probably due to kind of like the burst of activity on the C++ side that's been going on and is going to, keep on going, and a very, very slight dip on community issues and reviews that we would like to see trend up. So these are kind of like the, roughly the major initiatives that, we have to increase participation. If in case it's not obvious, we want basically everyone to get involved at the code level, if you have that capability and interest. And so, if you have Java skills or C++ skills, or even JavaScript skills, there's work for you to do on our project. And the Presto project is a terrific place to add a code contribution. It has so many stars and has such visibility that I feel like it's a really great place to do open source work if that's something that interests you. And so if you're interested, there's a lot of ways to get involved with the project. To start with, I would recommend that you pay attention to our GitHub boards. As I mentioned, this isn't really complete yet, but we do have a lot of kind of like good additions already. So we've started to really systematically start to categorize the needs that we have on things such as Iceberg, documentation, optimizer improvements, and we're going to be adding and also C++, in particular scalar functions, and we're going to be adding a lot more. So if you would like to get involved and submit some code and you just don't know where to start, our GitHub boards are really a really great place because number one, if there is a GitHub board for something, it means that it is important. And then two, within those GitHub boards, we're also starting to prioritize the work. So like if you click into them, often you'll see that there is a prioritization for the issues that are in those boards. And so hopefully it gives you a sense of what's worthwhile and what's a worthy contribution. And in particular, docs and flaky tests are a really low barrier way to get involved with the project at a code level. There's lots of documentation work, and there's a few flaky tests that we would love to get fixed. So those are kind of like great entry level ways to get started. In addition to that, pop into the office hours, and you can just basically ask how you can get involved. There's probably going to be someone who is at those office hours who knows what's going on and can give you more direct guidance. As you read the documentation, you might wish that you saw something, or sort of like see a typo, or wish something was a little bit more clear. That's definitely a great way to either open an issue to point that out or submit a PR to fix it. If you encounter a bug, in particular in the C++ eval, that's like very fast moving and lots of kinks are being worked out, definitely file an issue. And then like finally, as I mentioned, working groups are a really terrific way to get involved with the project without kind of like getting overwhelmed. We're going to be adding a few more working groups, but we already have 3 for security, architecture, and C++, and those are really kind of like terrific ways to get involved without having to know everything that's going on in the project. So that's it on the community side. I just wanted to end it with kind of like very, very high level roadmap on kind of like the big stuff that we're working on. I think at the very top is working to rewrite the C++, the eval section of Presto and C++. So there's a lot of work going on in the C++ section of Presto, and then also in the vlogs project to just kind of all make that happen, both for streaming, so like interactive queries, and also for batch queries. So if that interests you, definitely join the C++ working group. There's a ton of stuff and that needs to happen, and there's a ton of issues that you can just kind of like already pick up. A few others. We recently completed a history-based optimizer, but we're also enhancing the history-based optimizer with additional optimizations. Right now, it just works with join reordering, but we're going to be adding future enhancements to that optimizer in the future. There's a lot of work ongoing with Presto on Spark, and in particular, Presto on Spark when you use the C++ eval. So think something like somewhat equivalent to Photon. Improved lakehouse table format support. So there's a lot of work ongoing to close some of the gaps around Iceberg, increase our Iceberg support, kind of like make that a little bit more complete. And then also a lot of ongoing resource management related improvements that are getting added. And then on top of this, bug fixes, documentation, testing fixes, and things of that nature, and releases. So wanted to, point out again, PrestoCon December 5th through 6th. Definitely, think about attending or speaking. Submit your RFP if if you have something that's interesting, and definitely reach out. The Presto DB Slack. If nothing else, just join the Presto DB Slack. you can always ping me, and I can, give you a kind of like a dedicated intro. Thank you.
Thanks, Tim. Any questions before we move over to Joel and Vikram? All right. Feel free to post questions in chat if you want. But next up, we're going to have Joel and Vikram from Compute.ai sharing a little bit more about what they've built with Presto, why they chose Presto, and everything that goes along with that. So I will pass it over to both of you to take over.
Thanks, Ali. And I think Vikram is going to share his screen in a minute here. And while he puts that up, I'll just do a quick introduction. So my background, and this is sort of tied into the background of Compute.ai, the origin of this really goes back over 10 years. Vikram and I met when we were working at a company called Fusion.io, which was solving memory efficiency problems. If any of you remember Fusion.io, we were the self-described pioneer in the SSD space for enterprise. So we would put an SSD into a server and the database would go 5 to 10x faster right away. And in doing so, we were sort of unlocking the power of compute. SSDs were only 2 to 3 orders of magnitude slower than memory, while hard drives were about six orders of magnitude slower. So memory wasn't big enough to handle big database workloads, and the early results were pretty compelling in that space. I would venture to say that this was the beginning of the separation of storage from compute, where storage and compute can be scaled independently for price and performance. Over the last decade, we've seen the evolution of these large-scale distributed shared memory systems like Spark and Presto and Trino, and those are showing incredible in-memory performance. However, in-memory systems also come with their set of trade-offs, and that includes worsening core memory ratios in modern-day processors, and increasing cloud costs too. So fast forward to today, where we are. Vikram and I just recently rejoined forces a couple of months ago, and Vikram has been working on this new kind of database architecture, which takes advantage of distributed memory systems, but also integrates vertical memory efficiency and the hierarchy of SSDs. And he'll talk a little bit more about that as he goes through the presentation. So I'm going to hand it over to him in just a second. But I want to communicate with you guys really the vision of where we're going with this. We want compute to be completely abundant and separated from data management. We want to spread it everywhere. Data is kind of going everywhere in organizations, and you're seeing that with Presto, you're seeing that with Spark, you're seeing that with Trino. We want to match that with compute. And so what we've done is we've really separated it from the data management layer. And what that means is high amounts of concurrency, high reliability, and just massive scale. And the reason why we have AI in our name is because we believe we can be part of the community that builds the software infrastructure to support AI type workloads. So that's kind of in a nutshell where we're coming from, and a little bit about my story. I want to give it over to Vikram to share a little bit of his background and then take us through the presentation. But just want to say we're really excited to present to the Presto community. This is our first foray, and we're still learning about it. So as you mentioned in your opening, people joining the community for the first time, like we want to get involved and we want to see how we can give back. Vikram, are you ready?
Yeah, I am. Can you folks see my screen though? I have had some trouble here on the desktop.
Yep.
Yeah. Okay. You see my full screen. I cannot go into the presentation mode. It seems to just take over and then I lose track of the,
Yep, we can see it.
Awesome. So I'm Vikram Joshi. Thanks, Ali, and thanks, Joel here. I'm going to just, if it sounds like I'm speaking fast, it is because I would be. There's a lot of ground here to cover. Very thankful for the opportunity and super excited to share what Compute.ai is doing. Let's jump into a few slides. There's a couple of demos here we want to jump into. Want to thank Presto, actually, in fact, 12 years ago at Facebook, taking the lead for breaking data through the confines of data warehouses and those brick wall gardens, spelling them into files and showing how ad hoc querying could be done directly on the files. So I do want to mention that here, with Compute.ai, we are standing on the shoulders of giants. We'll be talking about Presto, Spark, Trino, all of it together. For us, you'll see how we are sort of agnostic to, but we leverage all of these technologies, and our goal here is to actually contribute back. So our customers are getting educated that data does not really, most of your data, it's in passing, it's ephemeral, it does not really belong in a data warehouse. You can hit it pretty damn hard and get the in-memory and the database and the data warehouse style performance directly on files. Thanks to technologies such as, Iceberg, between Parquet and Iceberg, you can actually take things a lot further, pretty much do everything, the point in time, flashbacks, recoveries, just checkpoints, all of the functionalities available, and we play into all of that space. So jumping on forward here quickly, what our idea for Compute.ai in the background is, we already talked about, the ecosystems that we play in. We're going to show you the demos in these ecosystems here real quick. There's a whole bunch of demos. So we are hoping that in a following, meetup, we'll be able to sort of build up. We'll do the introductory demos here just to introduce the technology so you get a sense of what this is. And it also opens up the conversation about how our C++ based code can be leveraged by the Presto communities and also Spark. Trino. So coming back into this, we play at the juncture, we play at the confluence of relational compute meeting AI/ML. What does that mean? So we didn't want to come out here. It's like being the 10th search engine and not doing something fundamental and game-changing like what Google did. So being in this space, and in terms of my background, I think I'm mixing things up here. I'm a programmer, and my past lives prior to being an entrepreneur, this is my fourth startup, I started my career at Sun Microsystems, Silicon Graphics, and Oracle, had something to do with Exadata. And since that time, making databases lightweight, you want to be light-footed and fleet, and you want to really make compute abundant. There should be compute for all. You should not have to think about it. And what does the confluence of relational and AI/ML really mean? We believe there's two main consumers of compute are going to be on the planet. And if you look at the number of server watts which are dissipated, it's going to come in from relational algebra. It's going to be everything that we do, with our relational, filters, aggregates, sorts, joins, maps, group bys, merges, unions, evals, whatever you name it. We talked about that. Tim mentioned some of these projects. Super exciting to hear people talk about this kind of stuff. And the other side of it, which we hear about, AI/ML, there's a lot of spotlight and the focus is on, generative AI and LLMs. There's, we believe there's so much more out there in that space that's happening. CPU, GPU, GPU, TPUs, whatever DPUs, whether you're shredding Polygon through AI/ML or you're doing relational algebra, you want to work there and you want to create immense value out in that space. And how does that work? I'll give you a very simple example. Presto does it, Spark does it, BigQuery does it. All these standards have it. You can invoke an UDF. You can take a model, an operational AI/ML model, and you can put that into production. What do models need? They need curated data. They need rows, columns, tables, arrays, tuples. You want to feed them in parallel, large numbers of models. So this is going well beyond, an OpenAI or a Bard or whatever. There are sources of compute, but by the time AI/ML models, understand, a whole decade we've seen of data scientists, beautiful work done out there with the Spark platform, with other platforms which allow you to build those models. They need to be put into production. They need to be operationalized. What better platform than to use SQL, which is a feeder of these rows, columns, and tuples in parallel. So this is that space where we play in at the juncture of CPU memory, the core to memory ratios, and feeding these GPUs and keeping them fed and allowing those operational models, which we have yet to see. An LLM is not going to help us with a fraud in a large bank, right? So there's so many more models out there to differentiate between apples and oranges and whatnot. That's what we are after. So once again, didn't want to come out there and say, oh, here's a better Presto or a better Spark. Absolutely, non-go. So I want to put that disclaimer out there. What we are doing, we are a business too. And we do talk about, committing back to open source community. I'm new to this community, in full disclosure again. And I feel we are very warmly welcomed, and we are looking at a path to figuring out how we can contribute back into the community. So Ali, Tim will be having a conversation, I'm pretty sure. And Steve Meehan, I want to thank him too for warm welcome here and introducing us to this committee. We have been following, we've watched all the GitHub check-ins because we do leverage some of that code, and we'll tell you the technologies and how we leverage that code. So our goal is to go out here and target use cases of customers where they find the current solutions suboptimal. So for example, compute for the semantic layer, right? There's a lot of work happening in the ELT space out there. Do you want to use a data warehouse for God's, cloud data warehouse for God's sake to do this kind of stuff? And then you have customers, bitching and moaning about, pardon my French here, about the cloud costs. It's burning a hole in my pocket. Addressing coders here primarily, I believe, and with due respect to others who don't code and are part of this. So coming back to that, massive amounts of compute is going to be needed. You have Iceberg kind of standards come in, you have the data dictionaries, you have all of this stuff which is happening here, and these thousands and tens of thousands of joins that need to be parallelized. That's what we focus on. So as that semantic layer, as you go across these silos of data, hopefully everything's going to be Parquet, Iceberg out there. That's the future that we envision. You want to provide the compute for that, and you want to make that compute dramatically cost efficient and create value for businesses. And you want to be able to avoid provisioning for the worst case memory needs. But in memory, we got some great, the progress in the last year has been immense. Awesome, good stuff. But now we have to go beyond the in-memory. We have to deal with the OOM-kills. We have to deal with these workloads where you don't have to provision for the worst case, and you're left with what? Distributed shared memory systems with 30% CPU utilization. And these are the customers that we are talking to. Hey, how can I reduce my cloud data warehouse costs? Can I increase my CPU utilization? And also try and get in-memory performance when I get there. I think I'd be preaching to the choir if I mentioned that, unlimited concurrency, that's sort of a dream, or whatever you want to call the holy grail of this. Databases and concurrency don't go together. They fight each other. They're at loggerheads. So what can we do about increasing the concurrency? And there are certain kinds of applications that require that. Again, hats off to the Presto community for demonstrating through their work at Facebook the kind of concurrency that database kinds of workloads. When I say databases, I'm talking about relational algebra. Never seen before. Unprecedented level of concurrency. Now we want to take that to the next level, and we'll discuss how our architecture actually goes ahead and does that. I need to go faster here. So we talked about this. Today we support both Spark and Presto dialects for running on this stuff. Again, the goal is not to create another engine which is competing, but think of this as the vlogs library. We're just starting. I saw vlogs on Steve Meehan's shirt and said, great stuff here. Think of this as a library, and creates value by just plugging it in. You can run files directly. Run SQL files and external tables. Same exact tool chains. We use, so open source Spark, JDBC drivers. Everything is open source. The demos you'll see is open source. So it's just our library that goes and plugs in. It's multi-cloud. It's on-prem here too. So our focus here in our C++ code is to address the core to memory ratio, which is getting worse here, right? The amount of data is increasing. You're having, to build the semantic layer, you're going to have all kinds of cross joins and whatnot, Cartesian products. There's going to be some explosive stuff, massive compressions and rarefactions in data. You want to be able to go and address that CPU to memory boundary. And that's what we primarily focus on. There's secondary and tertiary things that we do, but the focus on core to memory ratios, we believe is going to, and actually does, which you'll see as proof points through a demo, can dramatically increase the performance. So what you do here is, we won't get into the inner workings of how that is done. Hopefully you'll have access to the code and you should be able to see it. We can do further talks on that depending on the interest, but it's all about vertical memory integration. And my entire past lives have all been about doing distributed shared memory, and I love doing that kind of stuff. Here we took a different tack. We are leveraging the advances in technologies and services provided by cloud infrastructure. So you have distributed shared SSDs, right? The days of those, I shouldn't call out names, but, EMC kind of hardware, amazing stuff, great stuff, NetApp kind of stuff. But now see what clouds have done. You have infinite scalability at the S3 level, at the elastic file system level, right? These are SSDs with different tiers. We want to be able to leverage that. And instead of going on horizontal with distributed shared memory, we are more tightly vertically integrated and do demand paging across, do memory management and data management across the 4 tiers of memory hierarchy, which is DRAM, SCMs or storage class memories, flash and disk. There's no spinning media, so disk is just 2 layers of SSDs out there. And how do you manage the data across that with 100 to 300x overcommitment of memory? So we're not talking in memory anymore. We are talking, you're going to see this right now in the next several minutes. We're going to run like 100x overcommitment of memory. And for most modern day workloads that we are seeing in the BI space, at about 10x overcommitment of memory, this system actually runs beautifully. You don't sacrifice performance. If you increase the query complexity, right? If you increase the joinery in the system by some of these difficult skew kind of problems, just about everything that we're going to show you in the workloads is going to be skewed. It's based on customer data that we have permission to use. This is not proprietary data. It's stock market data. We do work with Wall Street banks. In fact, the genesis of the company was an upcall from 2 major Wall Street banks who said, hey, we are Presto lovers, we are Spark lovers, we do all of this. Can you make it a little better? We have these pain points, right? This is what's happening. We have large numbers of users working on here. There's 500 users using 100 node, Presto cluster here. We don't want the OOM-kills. We want higher developer productivity. What can you do? And the cloud costs are pretty high too. So help us out here. So we said, okay, let's address a point solution. That's why this conversation, that's why we're here. Okay, so come back to this. We discuss all of this. I'll give you a little bit on the caching. We're not big on caching, but we don't do front-end caching. So this is not about, again, due respect to all the caching technologies out there, putting a cache, a Luxio cache, great cache, very popular out there, but that fronts the data like between S3 and your compute like EC2. I'm using Amazon jargon here. So we do the caching on the backend, and I'll show you a picture in the next slide. The backend caching it's not a caching of the raw data, it's a caching of all of the curated data, your table data, right? All your logical data. And like you build a CTAS table and that data and caching it on the backend and standard stuff, right? Result set caching and query caching. You can do that and you can throw a bunch of solutions of caching. We haven't tested with Luxio, but we do 2 other caches out there, but it's outside of this conversation. And then we also have very predictable performance. So there's a database hypervisor that's built in here. Think in terms of like a VMware style hypervisor. Again, a lot of tech in there, but without taking you to the weeds, we can give very high level I should say, very sophisticated SLA. So you can actually partition a whole cluster and divide it any which way you want. You can say 60-40 division of work, CPU, memory, IO, and you can say 60% for my ad hoc users and 40% for my batch jobs. We believe we do really well on batch. I heard Tim have a mention of Meta being interested in batch. If that was about batch jobs, then I think you may be excited to see some of the work that we do on batch. In fact, the revenue that we are making is actually in the space of batch. We don't really care whether it's batch or ad hoc or whatever it is, a mix of the two. But because our technology is actually orthogonal to the all, we hope it, sort of lifts all boats kind of a thing. So that's where the caching is. Good SLAs out there. And we are 100% open, and we're also talking about contributing back to open source. This is an architecture picture that you've seen, maybe not in the same form here. Do you folks see my highlights here like this?
Yep.
Okay, cool. Thank God. I'm glad. So something's working here. So this is your EC2 layer. That's where the Compute.ai nodes work. We view ourselves like an operating system. So in fact, Presto is like an operating system. You just toss these containers everywhere. You shouldn't have to think like, today I'm going to install a data warehouse. Put it all in there. This is your classic S3. Here you have distributed, file system, which is higher, better performance with better SLAs given at the hardware level by AWS at least, your EFS out here. And your S3 data can be read, Parquet, Iceberg data can be read. You can do all of the compute out here. And your tables are written out here. They could also be written out here. We don't really care. But most of our customers like the price and the price performance characteristics of EFS. So we actually put our shared tables out here. So let's say we build many terabytes or a terabyte or petabyte, whatever size tables, CTAS tables. Now you can come out here, and I'll put this into words. This is all getting recorded and gets referenced. We'll be able to scale this thing to whatever numbers EFS can scale in terms of concurrency for real world BI workloads. And I think we have numbers such as 100,000 concurrent users have been tossed in, that there's a completely different level of concurrency. And I'll say that this picture is no different than a Presto picture or a Spark picture. It's almost identical in all ways. You guys have paging, we have paging. The paging that we do here to deal with the core to memory ratios is done at a completely different granular level. So this is all just-in-time paging. If you're going like 10x, not even 100x, at 10x, at 100x, things get really get out of hand. You want to be able to throw data out of the memory. You want to be able to pull data back into memory just in time. So we call this just-in-time demand paging. So this is not happening at Parquet row groups. This is at a coarse grain level. This is happening at some arbitrary, random granularities of different page sizes that are getting demand page based on the logical plan and based on this physical plan execution. So today we just use Catalyst. Tomorrow we'll also be using to support the Presto. We do support the Presto dialect, but that's through a simple LLM translation, just to show that we can support different dialects. But naturally, you want to be able to use the logical compiler of Presto. We'll need your help on doing that. We can work together on figuring that out. But that's not the focus of what we're trying to do. To stay alive and to stay in business, we want to be a part of this infrastructure because that's what customers are looking for. Hey, can you, I love Presto. Can you make it a little better at the risk of repetition? So that's the space that we play in. So the paging happens just in time. You cannot fetch a data in memory a millisecond. A millisecond is way too much time. At that time, you'll be thrashing. So how do you sequence your data just in time? And how do you, and this is not about historic learning. This does not use your normal computer science algorithms because those algorithms are tried and true, tested, and they won't work in such kind of thrashing systems. So this is all pattern recognition. This is all AI/ML-based models, and this is AI/ML-driven infrastructure, both at the physical lab plan level, the way the microkernel is run. Even a context switching is completely different. It's TLS-based context switching. We have some patents which have been issued, some which are in the process of being filed here. So again, it's taking you under the covers into the weeds. Let's look at the demos and see what the system looks like. And it's all about this just-in-time demand paging to manage the core-to-memory ratios to allow these massive levels of overcommitment without getting OOM-killed and giving you acceptable, good performance. So this is not about cheaper, faster, better. This is not saying, oh, you'll save 5x in hardware infrastructure costs. Actually, we do. We reduce the hardware infra by about 5x while not sacrificing performance. So it's not saying you're going to get 10x performance better. So the focus is more on reliability, condensation of condensing your cluster sizes, reducing the infrastructure costs, being more memory efficient, and putting more oomph into those cores out there. And finally, is there one more slide here? Differentiation. It's that extreme memory efficiency, vertical integration, and instead of going distributed shared memory, going distributed shared SSD, right? We want this kind of an architecture as a parallel architecture to what Presto Spark communities already have. We have in memory, now add this, and if we can combine both, we can combine both these architectures, how cool would that word be, right? Well, and that's what keeps us going, my team and I going. We're very committed to make the world of open source, basically it's not open source as much as making open standards open. And if open source is the conduit to that, great, we'll go ahead and embrace that. So that's what we're talking about. It's a specialized tool for those complex joins. So you want to be able to deal with the semantic layer, whatever you want to use. You can use any front-end tool that you want for your ELT. There's many out there. Some more commercial than others, but you want the compute for that. That compute is what Compute.ai does. And then you want to be able to feed that data to these parallelized models. And we are talking beyond generative AI and LLMs, like I mentioned here. We are talking about operationalizing those millions of models which have been built out there. And today, guess what? Unbelievable as it is. That's how it's run there with Python code. You're taking a stream of data a few gigabytes of data, trickling that through some Python code and running a model out there and feeling good about that. No, we got to change that world. Your models have to be run as a part of your queries. They have to be run as parallel UDFs. They have to be able to super recruit those NVIDIA GPUs or ARM processors and Intel processors and manage the DRAM and video DRAM boundaries really, really well. The ability to feed this data, whether it's a stream, a column which is a terabyte in size of many columns in parallel, that's what these models need to be kept happy. They're hungry, they're vicious, right? Their needs have to be fed. That's sort of where we are going out here. Let's look at the demos here. I'm going to end the presentation here now. And my apologies for speaking so fast.
We'll see if we can pull the demo off. It's 7 more minutes. This will be a record.
In 7 minutes, I'm going to do 2 demos, and this is cutting down on 1 demo. You guys can still see my screen? Reasonable resolution?
Yep.
I got these programming coding screens that go from eyeball to eyeball, so I don't know what the resolution looks like on Zoom. Most people usually complain, but I'm glad. You guys have good eyes. Thank you for that. All right. So here, what you're seeing is let's take a look at this. This is my I have an Amazon cluster, and this is your orchestrator, your coordinator, master node orchestrator. It's just a Spark JDBC driver, stock. So we do use, aside from SLAs, where we use some database hypervisor technology that we have, we also use para-virtualized interfaces. So we have not gone ahead and changed open source code. So we work side by side with open source, dynamic linkage, para-virtualized interfaces. So you can actually take a Spark container and add Compute.ai by their side, and the whole thing just works. That's sort of what the space that we're working in. So this is a 5-node cluster, which has come up, and we'll get this cluster going. And this cluster, so easy to start. By the way, we are also on AMR. So the reason why we play in the Spark ecosystem, Elastic MapReduce, right? So actually, Amazon hosted that whole effort for us and took care of they paid for it. And we, along with Presto and Spark, Compute.ai is not publicly available as a private offering on EMR. The reason I brought that up, it's not a business pitch here, is because architecturally, we mate with that system. So we don't have to, if you go on to EMR Spark, it takes 8 minutes to start a node. Why? You have to provision the Hadoop system, you have to do the file system, there's a yarn thing, and all of that takes cycles. Here you're going to see EMR clusters running. This is EC2, sorry. They're going to be coming up within seconds. We're going to kill nodes. We're going to run loads on this, and you're going to see the dynamic nature. This is how we think the world ought to be. Very dynamic compressions and rarefactions in your data, in your number of users should be reflected in my EC2 nodes with containers popping up very quickly and getting QS'd when the load goes down. And if things die, let's say I'm using spot instances cheaply, inexpensively, and they go away, guess what? My stuff should be fault resilient. And what we have done is we put in some extra additional bits out there into the what I call our orchestrator, which is the master coordinator node where the JDBC server runs, to make sure that this whole thing is fault resilient. So we are saying that this is a cluster with minimum of 1 node. So when nothing's happening, go down to 1, it could be 0, and a max of 5 could be 1,000 nodes, 10,000 nodes. We don't really care because compute should be everywhere. Let's not think in terms of a cluster, because this is not sort of a lassoed cluster, a tight view of the world. It's a super loose view of the world, but absolutely consistent data. Remember, I got my roots, my whole DNA is all in databases. So it's about never say die, robust and reliable, correct code all of the time. So this is this cluster that's out there. We're going to run a workload. So let's go ahead and see. Oh, by the way, this is your Spark dashboard. Look at port 8080. You can go to 8088 and you can see your Jupyter notebooks. We'll show you all of that, time permitting. There's no sessions here running here online. What we're going to do here is we're going to start a workload. Let's look at the 0 sessions are online. We'll start a workload, and your sessions to start to come up. There's just 1 node here. New nodes are going to pop up. We did have a screen out here that said that that minimum of 1 nodes and sessions per node was 16. So this system has been configured to run 16 nodes per session. These sessions are going to come up. This is just a random level. This is not a test of performance. This is just showing you scalability, how fast the whole system starts to come up. And with 5 nodes, you should be able to get up to 80 sessions soon. These nodes should be coming up to life very fast. Let's try and do a refresh. All the nodes are up. Now it's scheduling the sessions on that. This is just a Scala program. All these sessions are online, okay? And this is your Spark console pretty much. No changes from our code. You can go and click on anything. You can see the live performance. These are changes on our side. You don't see this in a normal stock Spark distribution. This is the Spark logical plan. Stock, no changes here. This is a physical plan, has nothing to do with a Spark or a Presto plan. By the way, you guys, we looked at your CBO. So cool, so cool. On the Presto side. Amazing work done in that space. So we don't play in that space, and we'd love to be able to leverage that or join forces there. But this is a physical plan, and for reasons that we mentioned, the way we manage memory, a physical and manage SKU handling, we have to do a very completely different physical plan. And you can see live progress out here. Let's go back to this cluster out here. This cluster is running. What we're going to do is we're going to be a little harsh here. We're going to take a bunch of these nodes, pick a number 3, maybe 4. We can kill all the nodes, it doesn't matter. And we'll just go ahead and, remember here, there were like 80 sessions, this whole thing running live 16 times on 5 nodes. So what we're going to do out here is we'll go here to our, let's go here to, can't type. Okay. So we'll go here and we'll pick a bunch of these nodes here. Okay. What did we discuss? 3, 4? Let's take 4. Otherwise you won't believe me if I kill them all. And what we'll do is we'll just go ahead and reboot them, right? We're just going to go ahead and reboot these nodes. And this is to show now, suddenly your load should come down to like 16 sessions or something. We may or may not see those numbers, but let's take a look here. So these sessions should be dying. There it is on 16. You actually saw this number, but the speed at which these instances are going to come back up and going to get rescheduled is going to be pretty rapid. And this is what the customers are looking for. I have massive worksheet data transactions coming up. My BI tools are running, right? I got Tableau, Looker, MicroStrategy, all this stuff, right? Trades are happening at the end of the day. This stuff has to happen instantly. So that's the kind of problem. Remember, we said we add value. We're not trying to replace an engine. We're just saying, make this better. This is how we are making this better. So your 80 sessions should come back up. And I know you believe me on this. So we'll just move on to the next. Okay, actually did it in time. So now here's what we're going to do. We'll go back and we'll just kill this workload. And as this workload is we just shut off the load, it should QS the system and you should come back. And this is set up for demo numbers. You can change the parameters. Oh, by the way, we don't have a user manual here. And somebody, Tim talked about the docs. We are thankful for the effort that you put into the docs because we leverage those docs. Our customers just look at the Spark Presto docs directly and all the information is there because we have not really done anything in that space. Everything that works should pretty much work here, give or take a little, right? We may not have the grammar, we may not have the latest eval work that's being done, but rest assured, the rest should just work. So if you look at this system should QS itself pretty fast. And what I'll do is I'll give maybe a minute here for any questions because now as the system QSs, we come down to one node. I'm going to show you the performance of a single node. This thing was just showing you fault resiliency, dynamic load balancing, and how this is robust and reliable, and how this infra using a para-virtualized interfaces has withstood the test of EMR itself, which was meant for maps and reductions, which was meant for a Spark-style architecture. By using a para-virtualized interfaces, we are able to prove much to, at least AWS is surprised and some others who worked along with that this can be done using this kind of technology. You can actually go, and this is a jig fit for those kinds of infrastructures. So let's see, hopefully the system is gotten QS, or it will after some time. I think there's a timeout out there. I'll give you 30 seconds or a minute for questions, and let's go to the performance of a single node. We're going to take a single node. I'm going to pound it harshly with some massive workloads, very arbitrary. It's my actual machine. These are very tiny machines. We're going to take a 16 gig 8-core machine, as you'll soon see, as here. And we're going to put some ridiculous amounts of workload. We'll go up to 100x overcommitment of memory. The amount of data that will touch in a matter of minutes will be probably hundreds of gigs and terabytes, and it'll all get paged, and it'll get demand paged to SSDs and different tiers of SSDs, working very small amounts of memory. Okay. Any questions here while I go to the single node?
Hey, Vikram, we do have a question in the chat.
Can somebody read that for me? Sorry.
Yeah, I'll read it. It says, we use Presto to retrieve millions of rows of training data for models, scales and performs well. Once we've trained and deployed a model, the client using it to get an individual prediction needs to pass a few dozen attributes. Lookups given a key. What kind of database or lookup table do we recommend for the attribute lookups? Athena lookups are way too slow. Postgres seems to work well for these lookups, but we have to sync the relevant tables in Postgres and Athena.
Oh, what an amazing question. This is going to take a longer answer than I don't want to be impolite. Can I address this community after the thing by email? Ali say yes.
She's giving me the thumbs up.
I want to say thank you. Thank you for the question. Yes, we'll get into that. We'll get into the UDS. We'll get into how to feed these UDS with the parameters, what exactly we do. And, we haven't done anything like brave and courageous, something new here in this world. It's just stock stuff. It just made it a little faster. Do understand that we are system software engineers, CPU, GPU, those kinds of people. I have like a whole company in this AI/ML space and GPU. In fact, work very closely with NVIDIA during the CUDA days when CUDA was being invented and we were trying to use it very early on. Brave and courageous, yes, that's stupid. Come back to this single node. Now we are down to one orchestrator and one server. We'll look at the performance of a single node, and we have a standard port 8080. We are looking at this. This is a lot of low-level microkernel metrics. But you'll see, stuff out here, for example, S3IO, Parquet files, everything is 0. It's a clean system. Nothing's been run on this. There is Iceberg here. This ICE Parquet. There's a whole bunch of Iceberg stuff which we're going to touch here. And we're going to be looking at this part of the screen. Because of lack of time, we'll just focus on this part of the screen. This is showing you bytes written to EBS. So remember, that's a memory tier over an NVMe bus, pretty damn fast. And this NVMe bus is stock EBS, stock infrastructure. Okay, just software only. And we're going to literally saturate that EBS channel on all these service nodes. Right now, it's a single node demo performance, right? And we're going to do like 100x overcommitment of memory. It'll vary between, 10x to 100x and even more at touch, and it'll go higher. And you'll see reads and writes going on to EBS, compressed data of different sizes all of the time using these just-in-time paging and AI/ML, okay? So I set the stage for that. Hopefully it works. It's worked every time I've been able to demo. So talk about, robustness and reliability. Here, this machine here. I don't think my highlights can be seen here. Let's go to a yellow one. How's that? 8 cores. This is just MP stack. You have 8 cores here. We'll try and look at this part of the system, which I hope you folks recognize. And it'll be awesome for my team to hear it from you guys, that these IO weights that we see in Spark, Presto, and Trino, massive IO weights when you start to page. And of course, this is not complaining about this thing, but that's the thing. That's the pain that we addressed out here. This number should stay close to 0. Otherwise, we are not doing a job, or rather the software, the algorithms are not working. And all this while happening, this is IO top. And you should see here are the disk reads and the writes. These channels are going to be busy all the time. And you should not see a blip. Your CPU usage should look good. And while we chat here, let's do this. Okay, let's go ahead and create a table for, this is nothing, just creating a simple table. Everyone can do it. And this table is just, it's stock market data. It's loading this data into this tiny machine, which was just 16 gig of memory, which started off at about 13 or so, I think. And there are just 8 cores here, tiny little machine. This is just like Presto, Spark, everything. They do the same thing. Nice idle, Presto has beautiful patterns out here. Everything looks good until this memory starts to go down, right? So this is at about 3 gig of memory. You should start to see IO here to paging, just the start of this thing, okay? And this moves very fast. That was 1.5 gig, just written very fast. And let's focus on this IO weight. While this is happening, you should not see a blip. And that's your AI/ML stuff just in time. And this is working at 2 levels. It's not just demand paging. The physical plan itself knows what data is being touched. We're not doing historic, smartness out here. This is just right there on that plan on this data. This system does become smarter with the workload, but that's just marginal stuff on top of what we actually do. So this table is going to be created. It looks like it's trailing the last few Parquet row groups maybe. And as this finishes, we are going to start the real demo. Okay, we need an initial table, a CTAS table, and look at these reads and writes going on. Look at 0 IO weights out here. It's constantly at 3 gigs of memory, very low. You won't even see the blip here because you're trying to do this and schedule those cores out there, right? You don't want the memory, there's so much data that needs to be accessed. You don't want your code to be stalled reaching memory. That stall looks like idle CPU. So it's the prevention of stall in using that to do IO, using that to do compression, bringing data just in time, paging stuff and evicting data that you don't need out there, right? So this table has been built. Now let's go ahead and have some fun with some of these tables. We'll go ahead and create another table bar. It doesn't really matter what these queries actually do.
Hey,
but,
Tim is asking if the CPU load is spiking. He says he's not seeing it in the top.
Oh, what do you mean by spiking, Tim?
Meaning like I see CPU percentage, but like what happened? Like what is the operating system reporting for load?
Oh, for load. I'm sorry, I don't understand. The CPU is right here, right? So 100% CPU usage. That's not what you're looking for, Tim?
Right, but like a load would be like there's like 100% utilization, but there's also like this, like the operating system has like
this load. You're talking about this load here.
Yeah.
So
yeah, exactly. Okay.
I see. Goodness, there's still people who use the canonical load form of Linux. Okay. So right now it's low. We can look at this number. I haven't been looking at this, but overall the system is, through various different metrics, looks pretty saturated. I'm sorry, I don't think I answered your question with that. But let's look at that load now. I'm curious. I'm going to throw a bunch of stuff. These are my 4 windows here, just beeline windows, command tools. And here, I'm just going to go out here. I'm going to create like a cross join of 1.3 billion rows, massive amounts of data. This is going to just beat the system really bad. Let's go here and do a couple of things here. We'll create another CTAS table. We'll run one of these customer queries. We'll look at the query plan as it's getting executed. We'll run this thing in the interest of time. What I'll do is, this is a dumb, scrub the disk. Like this is SF1000. So it's taking like a 700 gig line item table just to keep S3 busy. So S3 is being busy, just arbitrarily doing a full scrub, reading all of the data, right? Pointless thing. You're just doing an average on all of the column. It's forced to pull all the data and you can't use any metadata, no Iceberg, nothing. And here I'm doing a join. And now let's see what's happening. CPU should look nice and busy. You should not see any IO weights. Your memory is generally kept at a good threshold, and you should have constant reads and writes going on. And that's all the scheduling voodoo that we go after. It's one of the things that we do right there. Okay. So this workload is running. This system has no IO weights. Your load average, these are the numbers here, whatever that is. All right. It's been a long time since I've looked at this load stuff. I have to go back and look and see what these actually mean. Unless Tim, you offhand can tell us what's going on.
It's like the difference between like the saturation of the CPU versus kind of like the backlog of work that this CPU has. Okay. So like the amount of waiting before it reaches the CPU. That's my off the cuff explanation.
Good stuff. Always good to be learning. All right. No, thank you for that. So no idle, that's what we're looking at. We're also looking at the system time here, which generally you can't do much about, but again, the way the C++ code is done, almost, I come from Oracle, rewrote the runtime out there. We bypass the whole Linux kernel, basically take control of the whole thing in user land. So that's the model out here. So you get very little system, but the key here is no IO weights, very nice CPU profile, user profile, constant reads and writes going on out here. And let's take a look. Oh, we forgot this thing, all the coolness here, right? So this is your SSD reads and writes, which are going on, like 130 gigabytes written. You're seeing that a lot less is written, and over time, a lot more is going to be read back. So the same data is going to be read many, many times over, unbeknownst to you, and it's going to work on it. So all the way we page, the way we manage the metadata for paging, if someone's doing some operation as a part of the plan, how do you get that data and exactly what they need, the tuples in the rows in time, and feed it to those cursors as they are getting scheduled? That's why the physical plan changes completely. We cannot use anyone's physical plan, but we do want to use the Presto logical plan because I think it's much better than the open source Spark at least. And here is your dashboard. Let's take a look at some of these queries that are running out here. Let's go here, and I think we may be approaching, someone's going to say timeout, but allow me to just finish this one thing. Come in here. Let's look at one of these, queries out here, and take a look at this. This is the stock. This will look just like Atlas. Like I said, we don't change anything here, but our physical plan is going to be very different because of all of the schedule. And this is a pretty, hey, let's stop this 5-second auto refresh here. Let's take a look at what's happening. It's going to get refreshed. So there's a massive number of cross joins, and truth be told, this thing instantly crashes Spark and Presto, Trino, everything. I do have some feedback. My team has some feedback on Presto. We actually have a whole bunch of stuff we can actually give to you. There's some simple stuff, so low hanging fruit that we can do to Presto to fix like a simple accumulator and aggregate right now. The more I increase the data, the more I touch it, just kills itself. Should not happen. This stuff is very silly. If you look at the code, we can fix some of this stuff. But anyway, these are some massive left out of join 11, 9, or some big number like that, touching a lot of data, many, millions touch, billion touch. It does not matter. I know you trust me already in the short time. But the bottom line here is that this system is going to run, with minimum to 0 IO weights, manage very little amounts of memory. This stuff can be run in 2 gigs of memory. It can be run in 8 gigs of memory. It can be run with whatever cores. And now you can throw any amount of compute as you want, and you can dynamically scale it. So I think that's sort of, I'll shut up here. I'll open up, some time room here for questions. But we can look at the system in the background so that you can see, how it's running. It should all finish over time, and large amounts of information is going to be touched and read and whatnot.
Awesome.
Thanks for listening.
Vikram, thanks, Joel. So I know we are 15 minutes past the hour. If you need to drop, we get it. But I think Vikram and Joel, you can stay on and take questions for folks that want to stay on and have any questions.
Thank you for sticking with us.
Yeah, before people leave, next Wednesday, 8:30 Pacific, we have our open office hours. So feel free to drop in. And if you're not in our Presto Slack channel, please join there, and I'll send the link out there as well. So thank you, everybody. This was a really great meetup to come back to. Again, we'll be doing these every month. But thank you to our presenters. I think Tim had to drop. Appreciate it. And feel free to stick on and stick around and ask Vikram and Joel more questions if you want.
Thank you all. Great to meet you all online. Yeah, I'm online here in case there are questions. We can jump into all of that.
So I think you can probably take Roger's question now if you want, if he's still on.
Roger here?
Still here.
Cool.
Let me take a look here at let me read the question back here. Srinath, looks like you were answering something, huh?
No, I was just asking about the C++ project board. This is more about using Athena for attribute lookups.
Yeah, I'm trying to find the question. Srinath, you want to start answering the question while I even look up to read it and parse it? I was in this demo. I'm scrolling up the questions here. I forgot to, Srinath, go ahead and start speaking to this and what we're doing. And K1, maybe you, or Hoon also, you're online. Any of you, jump into that.
So, I think the question is basically for ML. They're training using Athena. This data set is few million rows, and then the prediction happens using lookups on Athena, when Athena lookups are slow and PostgreSQL lookups are working well. So I think this, Vikram classic, UDF, how to scale running UDFs on billions and billions of rows, where you're training on a small amount of data, but operationalizing it. And how do you operationalize a model at scale?
Yeah. This is the crux of the whole thing. Let's start talking about the engine, how we feed this. You want to give it a shot? You wrote parts of the code. I'm happy to.
Essentially, the problem is, classic relational, you have tables, rows, and columns, and how do you run maps? And in the context of maps or filters, how do you run, your models and operationalize it? Vikram came up with, the previous company was Scalar, and we built an SDK basically for exactly managing that. How do you run, Python code at scale across, GPUs and tensors, and how do you actually scale that? to billions
and run it natively too, Srinath. We have to run it natively. So when on Google Cloud, we will super recruit TPUs as is. You can take a model, a TensorFlow model, and run it without a single line of code change, no APIs, nothing, as is. And you have to be able to run in parallel. But let's address this the issue about feeding data from tables. It's an answer which may not be intuitive, but I'll share this with you. And it surprised us too. And I think Srinath is sort of the authority on this. When you are running distributed shared memory, it's funny that we had this conversation with Steve Mee last night, right? And we're all nodding our heads. Even in a distributed shared memory, if you run a read-only workload, there's still consistency issues and concurrency issues. Consistency and concurrency fight each other. For read-only workloads, where's the consistency come from? There's a lot of data, monitors, logs that are being touched even for read-only stuff, catalogs, there's shared information. So scaling a distributed shared memory, even for read-only workloads, hits some concurrency issues. Now, when you are trying to take and parallelize a model and feed it through all of the cursors, that itself requires different infra, which we have, which is, I have these UDFs running. How do you run them in parallel? These UDFs actually don't have CPU, because your model is going to be fed to a GPU, and you're going to be able to give a single stream of data to this GPU, right? To this video DRAM. And now you have to parameterize and push this thing. So you have to keep your CPU cores busy. And because we are not distributed shared memory, we have the innate or intrinsic advantage here, right, by birth, that we don't have to deal with this consistency fights concurrency any more than what is required in a single node cluster. So in a way, we made the problem simpler for ourselves. Then we are able to just feed these rows and columns in parallel like a stream through this video DRAM interface using just parameters through a UDF. And that's sort of the essence of the whole architecture out there. And it just runs well. And the reason why we had to do that is, one is because we are working at the confluence of, relational algebra meets AI/ML. That we think is the future. Let's look beyond the AI, LLM models, which are going to be run by a few companies. And sure, does it need compute? Massive amounts of compute. But the amount of compute is going to be horrendous when we take all those models that people are building and start to put them into production environments, right? Those models are going to require a large amount of compute, and I can't imagine, it's not going to work if you try and feed it through Python. It has to be with SQL, because SQL is not imperative, right? SQL is declarative. So easy. You can describe what you want to do, join apples with oranges and filter them by fruit, or whatever you want to do. So easy. So using SQL as the infrastructure for deployment of these models is where we want to go. So this question hits us or addresses exactly the core functionality that we are trying to address. Is when I take a table like in Athena and put it into a massive cluster, it's everywhere. To access this thing in parallel is going to hit that concurrency issue. It's going to be slow. It's not going to be very easy. And we have the advantage of a memory model where we know how to feed this data firstly locally, and we know how to do this vertically in the memory hierarchy, because memory is only so much, but we know how to get it from flash and keep that system busy. Even though it's a single core, which is just pulling the data for a single column to feed a single model, this model is parallelly going to run and stay busy. Anything else? Or did that even make sense, I should ask?
So maybe Vikram and Joel, you can drop your contact details into the chat and people can reach out to you if they have more questions.
Yeah, that would be great.
Cool. All right, folks, thanks a ton for everyone that stuck with through the end with us. I know this was a long one, but I think it was really good. So thank you, Joel and Vikram, for sharing. I think it's really cool what you guys are doing and what you're building. Would love to see more on as you build out the Presto side of things, how it's going, and we'll stay in touch on that. Thanks, everyone.
Thank you again. Take care. All the other.
We'll see you at the next one, everyone.
Okay.
Thanks. Bye.
Bye.